Hello, and welcome to the second part of this series. In this video, I'll be deriving an expression for a rotometer. More specifically, I'll be demonstrating how the volumetric flow rate depends on the height of the ball on a rotometer. So first off, what is a rotometer? What is a ball doing in here? And what is going on? So to simply put it, a rotometer is simply a tubing. You have a tube, and within this tube, there is some sort of ball. Right? Simple as that, no reason to overcomplicate it, no reason to undercomplicate it. That's all you need to know for now, that there is a tube with a ball inside of it, and I'm going to denote, let's say that this ball has a diameter of d naught, and then that the actual tube has a diameter of d. This will come in to the equations later, but pretty much we have some fluid that's coming in and pushing this ball up and down around this tube, and then depending on its h, the volumetric flow rate changes. And so what this happens is we're going to be talking about three different locations. We're talking about right here, we can call this number 1, point 1 where we're under the ball, and then point 2 when we're going to the sides between the ball and the diameter of the tubing, and then finally 3 when we're at the top pushing down on the ball. And so we'll be deriving an expression so that we can demonstrate how the volumetric flow rate and the height are relate to each other. So starting off, we know that we're talking about an equilibrium, and so what we're going to do is going to write we're going to derive an expression deriving the force or the pressure force with respect to the mass of the ball. So what we're going to do for the left-hand side, we know simply that it is equal to mass times gravity, right? However, in this situation, we don't know what mass is. We're just going to be dealing with density. As we know, density is equal to mass over volume. So what I'm going to do here for the left-hand side, we're going to have density of, start off with the ball, and then multiply it by the volume. So we're going to have pi, then we're going to be using d naught instead of radius. So we're going to have d naught cubed over 6 multiplied by g, right? And then the other thing, we're coming from the top, we're going to think about buoyancy force, right? So if this is going to think about being positive going up, then we're going to have to subtract this other part, and we're going to have the same kind of idea. We're going to have density of the fluid multiplied by d naught cubed over 6 multiplied by gravity. Alright, then we can go ahead and rewrite this simply as change in the 2's multiplied by pi d naught cubed over 6 times gravity. Alright, that's for our left-hand side. And so for right-hand side, I said we want to equal it to the pressure force, right? And what that is simply the pressure times the area. So what we're going to do for the right-hand side is changing the pressure. So we have 3 and 1, right? So what we're going to write here is we're going to have P1 minus P3, right? And then we're going to have the cross-sectional area. And what we're going to do, we're going to think about just, we're going to make a circle in the middle of the ball so that it's at its max, so that this is pi d naught squared over 4, right? Then this is simply equal to this hand side, right? So this is at equilibrium, and therefore this is our equation. Okay. However, we want to be dealing with the pressure at point 2, right? We want to think about what's going on at this instance, because 3 and 1 is very simple. So what we know is going on here between 2 and 3, we know that it's going through a sudden expansion, right? It's going from a really small cross-sectional area to a very large one in a very short amount of time. So from that, we know that the pressures have to remain constant. We know that P2 is equal to P3, right? Because I said it is a systematic expansion, so pressures remain constant. We can go ahead and plug P2 in for P3 in here. So then we get P1 minus P2, and then I'm going to go ahead and multiply this out onto the other side. So then we're going to have this remains the same, changes in the densities. And then we're going to have pi d naught cubed divided by pi d naught squared. So we're going to have simply d naught. And then 4 over 6, that becomes 2/3. So 2/3 d naught times gravity. That is our equation for P1 minus P2, and that's going to come into help later. But for now, there is our equation. So now that we have our force balance equation, we can now go ahead and write out Bernoulli's equation for this instance, right? For what's going on in here. So, what do we know? We know, start off with change in pressures. So we know that P2 minus P1 is equal to change the fluid, or the density of the fluid, plus, I don't know what equal, and then with the velocity, so we're going to have V2 squared minus V1 squared all over 2, right? And this is equal to the negative frictional factor of force, right? However, since we know that this is an equilibrium, we can go ahead and we know that the thermal energy in this situation does not change, and therefore this is 0. Right? So we can go ahead and write these two out to equal each other. So what I'm going to do is V2 squared minus V1 squared over 2 is equal to P1 minus P2 over density of the fluid. So from here, what we can do is we can go ahead and simplify this, as we know that there is this fluid has equal density throughout, right? From 1 to 2 to 3, the density is the same. So we can go ahead and say that V1A1 is equal to V2A2, right? Since the density remains the same, we know that the volume times the area is equal to the one at the every location. So we can go ahead and rewrite this as for V1 to be V2A2 over A1, right? We can go ahead and plug this in for V1. So then we have V2 squared over 2, and then I'm going to go ahead and pull this out so that we have V2 squared over 2, this is 1, minus, and then V1 squared. So we're going to have this whole thing squared, V squared, we already pulled that out. And then we're going to have A2 over A1 squared. Right? And that is equal to P1 minus P2 over the density of the fluid. Beautiful. Okay. And then from here, what we can go ahead and say is we know A2 over A1. What can we do with that? Well, we know that the cross-sectional area of 2 is extremely small, right? It can hardly get through. And at A1, it's very large. So what we have here is pretty much a really small number over a really big number. If you go ahead and square that, you get an even smaller number, which pretty much you can go ahead and denote this has to be 0. So now we get v2 squared over 2 is equal to this expression. So then I can go ahead and rewrite it in terms of v2 simply by multiplying it by 2 and then the square root. So then we get v2 is equal to the square root of 2 p1 minus p2 over density of the fluid. Beautiful. Now, what can we do with this? So you can see what we worked out earlier, our equation. Look at that. We got p1 minus p2, and that fits perfectly into our v2. So I'm going to go ahead and rewrite this here and then kind of free up some space. So if we write this expression for v2, we're going to get square root of 2, then put in p1 minus p2, we put this expression in. So we're going to have ps and multiplied by 2 do, so this is going to be 4 do, and we're going to have 3 in the denominator, times g, and then rho f. Alright, that's our expression for v2, and then what we can do from here, like I said from the beginning, our main goal is to solve or demonstrate how the volumetric flow rate relates to the height of the ball, and we have neither in this expression, so what we can do is use it to write an expression for a volumetric flow rate. So if we recall correctly, we've gone over this before, the volumetric flow rate is simply equal to VA, right? And then the expression, this equation would be V2 and A2, on any of those positions. So we can go ahead and plug this into Q and then multiply it by A2. And what we're going to do for A2 is simply, like we said before, we have the diameter of the whole tube being D, and then the diameter of the ball being D naught. So what we can do is subtract these two to get the total area right here for 2. So we can go and rewrite this for Q. I'm going to keep V2 for now, so we can plug this in later. We'll write an equation for A2. So we said the difference between the two and pi r squared, so pi d squared over 4 minus pi d naught squared over 4, right? You're doing the change between the tube and then the ball. And if we plug in V2 into here, we go ahead and get Q is equal just going to rewrite this way, 4 minus pi d naught squared over 4, and multiplied by V2. So 4/3 of density of the ball minus the density of the fluid times d naught times gravity all over density of fluid. Beautiful. Okay, beautiful. So now we have our volumetric flow rate here. However, we still do not have it in terms of H, right? We're still missing that. So what I'm going to do is free up some space over here so we can go ahead and talk about this a little more, how we can integrate H into there. Okay. So, like I said earlier, this is just a very simple, dumbed down way of understanding what's going on here in this rotometer. However, this is not exactly what it looks like. I'm going to draw kind of a simulation of what it should look like, and this is a little bit exaggerated just to kind of give you guys the idea of what this looks like. Sorry. Marker's dying. so this is very intense, obviously. It is not as much, usually probably something like this. You can hardly tell, but for our purposes, for you to understand what's going on here and how to integrate h into this expression, this is what we're going to use. And what we're going to be using is a mathematical expression that we've been using since middle school, just simply y equals mx plus b. We all know what this is, and what we're going to be doing is be plugging in d in these terms so that we can plug it back into here for our height, right? So what we know here is as height changes, right, our d expands, right? So we can go ahead and say that y is our d, right, because that's what we're solving for. Then our m is just some constant. I'm just going to keep that really small constant m. For our x, that is what is changing, which is our height. Diameter is changing with respect to height. Then plus b. And then b is also a constant, which is the minimum at which it can start at. And if we think about this, you can think about it all day. There can be no minimum at which it can start at, but really, we're talking about a ball here. This rotometer, it has to fit in the rotometer, so the minimum that it can possibly be is d naught, right? So if it is any smaller, then the ball does not fit in the rotometer. So this is our expression for d, and if we go ahead and plug that into here, we can go ahead and solve out how h relates in this situation. So I'm actually going to erase this so you guys now understand. Just put a little bit more room. I'm going to have the front side out front. So we're going to have 4 rho b minus rho f d naught times gravity over 3 rho f. Right? Then multiplied by this. Now what I'm going to do is take out pi over 4. So that we get d squared minus d naught squared. Okay? Then if we go multiply this out, if we multiply d out, we get m squared h squared check. Yeah, I think this is just gonna. Okay. Yeah, I think this looks good. So if we square this out, we get m squared h squared plus 2m h EO plus d naught squared, right? If we go ahead and plug that into here, so that we get Q, this whole radical, 4 rho b minus density of the fluid times d naught times g, and over 3 density of fluid. Okay. And again, we have pi over 4 out. And then multiplied by this, we said this is what we get. So we get m squared h squared plus 2m h naught plus d naught squared. And then if you remember here, we get minus d naught squared. So these two cancel out. I'm just going to take it out, no reason to write it in our expression. Okay, we're almost there. Then, if we recall kind of what we did earlier, we know we said that we're using this mathematical expression. so that we know that m is a really, really small number. And if we squared this said really, really small number, we pretty much get 0, so we can go ahead and integrate this as 0. So that we can go ahead and rewrite this expression right here. I'm going to keep this still out in the front, so we have 4 times b minus f times d naught times g over 3 rho f, and then multiply pi over 4 times this, so we get we get pi m h d naught over 2. So go ahead and rewrite this a little bit better. I'm just going to erase this a little bit, just throw some space. Then we get q is equal, pull this out front so that we get pi m d naught over 2, right? 2 pi m d naught, and then multiply by this radical. I'm just going to put it to the power of 1 negative, or power of 1/2, so I'm going to have 4 density of the ball minus density of the fluid times d naught times gravity all over 3 times density of the fluid. Like I said, we have this to the power of 1/2 multiplied by our h. There we have it. There is our expression demonstrating relationship between the volumetric flow rate with respect to h. As if you can see, this pi m d naught along with 4 with these, all of this pretty much are all constants, and this demonstrates that the volumetric flow rate is directly proportional to the height of the ball. So there you have it. Hopefully this video helped you guys, and have a good rest of your afternoon.